points here. And at the end of last time, we're talking and making the case that indeed this expression here, heat output, rate of heat output, is a product of these terms, mass flow rate and temperature change. We closed off things last time by talking about how the temperature part of that is important and how we can define that. I was going to recap that today, but actually, because I thought I did a bad job at the end of last time, too rushed because we didn't have much time, but I looked at the video and it seemed not terrible. But I was going to perhaps revert to this. Some of you were here, not everybody, didn't need to be, but just to make the points, a couple of points. Actually, I was interested that I could hear myself speaking in the corridor, recorded on that, and about some interesting, I know exactly, the closed caption didn't quite capture it correctly, but I know exactly what I was saying. But the talk on Friday was interesting, and I don't know if I can, does it go full screen? Yeah, probably will go full screen. The thesis of the talk was to look at how thermal short-circuiting evolves in reservoirs. So the holy grail of trying to get EGS to work is, one, get enough fluid circulation going through it, and with that fluid circulation to make sure that the heat stays up, delta T stays high. The conventional approach has always been to look at, instead of hydraulically fracturing it, stimulating it less than the minimum principal stress, so you don't drive a hydraulic fracture, but you reactivate fractures in shear as a network, and therefore you get this volumetric penetration of fluids in a big volume with lots of fractures. The problem with that is that it's not brutish enough to be able to get typically big flow rates, and so this 100 liters a second that's needed to get a nominal 5 megawatts electricity out to be able to pay for the wells is tough to get unless you really go after it. And so conventional wisdom, I'd say now, with the Fervo cases and also with Utah Forge, is to really do hydraulic fracturing, really break the network up, and then see if you can control the temperature drawdown as it occurs in some way. And there are different methods of doing that. So this talk was talking about all the methods by which this early breakthrough occurs. And he's quite systematically going through adding each of these factors each time. So what we've talked about are maybe the first three of these. The idea is that you inject fluids. In the first time as you produce your reservoir, pressures are increasing within the reservoir as you're stimulating it, and then maybe drawing down as you're producing it. But the changes in stress, effective stress that you get by having fluid pressures dropped, increases in effective stress, mean that fractures will close and permeability shuts down and flow rates are difficult to maintain. As you chill it with cold water circulating through, what you'll do is you'll open up fractures. The ones, as we said last time, that, if I show this figure exactly, the point we made last time is the ones that take the most flow have this natural feedback. One is, if it's a rigid medium and nothing happens, then they'll continue to take more flow and they'll continue to get cooler and cooler without any mechanical feedback, and so the temperatures in the reservoir will drop quite quickly as those cold channels grow through. The feedback that occurs is that as you chill the rock, it contracts, thermal contraction. As the rock blocks on either side contract, the aperture gets larger, and because its flow rates are proportional to B cubed in that fracture, then there's this positive feedback that makes the cold fractures even colder and take more fluid. And so if you look at tracking behavior when you just had a rigid porous medium that had some big long fractures, which typically tend to be large aperture fractures, empirically, observationally, in addition to the fact that those long fractures have larger apertures and cool quickest on their own, the feedback of having the blocks that surround them contract and the fractures getting larger exacerbates the problem by making it cool even faster. And that's the feedback that can't be avoided. So the talk on Friday was investigating this from all the other things that could happen. So not only do you start off with large fractures that take large flow and cool fastest, because typically the conduction length from the next fracture or halfway between the next fracture is the longest for those long fractures. But you also have the effect of thermal contraction, thermoelastic effects occurring, which is a feedback. But also you get things such as mineral dissolution, mineral precipitation, and pressure solution. And so this talk on Friday talked systematically about each of those. And what his approach was doing modeling kinds of things that we're talking about here. Sophisticated modeling with a fracture between two wells embedded within a hot medium. You flow between those two wells, and you look at how the initial statistical distribution of voids in the aperture change over time, and as a result of that, the flow field is altered as different parts of the fracture grow and some contract, and the pathway that's depleted in heat, where heat is robbed out of the rock and put into the fluid, expands. And if it expands directly between the inlet and the outlet, then that is cold thermal breakthrough, and you might have a large volumetric flow rate, but you might be producing at no delta T. So you inject at 30 degrees centigrade and you recover at 30 degrees centigrade. And so what I thought he did a nice job of, if I can bring up the light, is successively looking at different processes. I don't know if he I can remember one figure that had them all. Different locations, perhaps I can't find it. Arash's propant idea. Yeah, it's earlier. Come to Peking. So perhaps I can't find it. I should have looked for the marker of where it would be actually. I guess I'd let it run. They would slowly come up. And so what he could do was individually look at turning on these prospects. And so all of these things are stacked. And so I guess perhaps I can't bring it up so successfully, but as you develop one of these reservoirs and start injecting, the first thing you'll do is you'll dilate fractures in stimulation, and then as you drop the pressures, those fractures will close and be relatively closed. And so that effect may happen in the first month or so. You'll draw down the temperature in the reservoir, and you'll get this thermal contraction effect occurring, maybe in the moderate term from months to maybe years. And then in the long term, you get the effects of dissolution and precipitation occurring. And so you could imagine those effects operating in a variety of different ways. And we won't worry about the equations, but I thought, actually this was pretty much the figure I was looking for. And so you can look at, if you dissolve material from the fracture network, you'll open the aperture up perhaps, and as a result get faster throughput. So that's one feedback, that'd be helpful. If you precipitate in portions of the reservoir, you'll shut down porosity, and that may be beneficial if that's a cold part of the reservoir, but might not be beneficial if it's a hot part, because you'll reduce the heat you recover. And this issue of so-called pressure solution. Pressure solution is where you have contacting asperities that are holding the fracture open, and as you as you apply stresses on this, the solubility of the point-point contacts across asperities is higher when it's carrying stress than in the unstressed part, which are the free faces. And so that effect means that the dissolution rates on the contacting asperities is high and will drive closure on those asperities and will allow the fracture walls of the open fracture to follow as that shuts down. So you get a whole variety of different effects happening at the same time. The feedbacks work on different timescales: pressure, short term; thermal, medium term; chemistry, perhaps long term for dissolution precipitation. And they act in varying degrees. Some are positive or negative. Some are reinforcing. So certainly thermal quenching tends to be reinforcing in that the large flow channels get cooler and as a result take more fluid and result in larger volumes, masses of cold fluid coming out of the other side. So that kind of is a segue into what I wanted to talk about today. If I do that. Okay. So this, I've lost it. This is what we talked about last time. I thought in retrospect, actually I did a better job in retrospect than I thought at the time. The idea is that for rigid media, and these analyses are for rigid media, no thermal contraction as a function of cooling, you'd like to be able to operate where the reservoir has a sudden breakthrough and ends after 30 years, if this indeed is 30 years. And the geometry of what that looks like in terms of thermal drawdown is that it means that you're depleting at the injection well all of the heat you can, and the water's carrying that heat to the production well. And so near the production well, the reservoir is still hot. The converse is that if you get a very fast flow through in this, it chills all the way along the fracture, and so all the fluid sees as it goes through the fracture is cold wall rock, and therefore cannot pick up heat from that as it goes through. So this is what you don't want. This might be what you want, because this would give you this, and this would give you this. And the ultimate extension of this behavior would be this, of which the best case is this step change in temperature as you go through. So long, the caveat is that the time when this occurs is not after 5 days, but after 30 years. And I just made the point last time that if you choose a flow-through rate, there are certain analyses. You can find the reference to this, actually this one, which is what it's taken from, to be able to show what these behaviors are. And in terms of non-dimensional parameters, typically the field results from Rosemanose is the one in the UK in the 1980s. Fenton Hill was the first one at Los Alamos, 1974 onwards. They both have flow-through rates, if you fit them to these curves, at something like these volumetric flow rates of 10 to the 2 non-dimensional parameters. So this is this. This is thermal conductivity of the reservoir, storage properties, thermal storage properties of the fluid, density and specific heat capacity of fluid, thermal conductivity of reservoir, volumetric flow rate, and the size of a characteristic dimension of the reservoir. And it makes sense that it's these mixtures of properties, thermal conductivity of the reservoir, because that's getting heat into the fracture, and that heat is being carried by the characteristics of the fluid as it takes it to the outlet well. And if you work on this as being a reasonable flow-through rate of 10 to the 2, QD equals 10 to the 2, these are the graphs that would represent 3 different scenarios where the spacing between fractures is big, and if you find QD equals 10 to the 2 on this would be 25, 10 to the 2 would be 100, so maybe it's this value here, which is not giving you early temperatures which are high. If you look for 10 meter spacing, you end up being on this curve, and if you look at even smaller spacing, you end up being on this curve as well. And so this is perhaps what you want. This would mean that the reservoir would be depleted of all the thermal energy in it after whatever this is, maybe 10 years as we said last time. So that's for a rigid reservoir in which you don't have this feedback of the big fractures cooling quickly and getting larger and then cooling even more quickly, cooling the flow even more quickly. And so when you have that feedback, it exacerbates that problem. So what we'll talk about today is the next stage on in terms of those feedbacks, and that is that chemistry has some importance in this. And so if chemistry acts to be able to change either the flow-through rates, so we have energy being equal to mass flow, the fluid that's flowing, and how much heat you get out of the effluent fluid. If chemistry seals the reservoir so you can't get this, then that's not good. If chemistry opens up the reservoir so you get higher mass flow rates under a given fluid pressure drop, you can only provide enough fluid pressure in the reservoir that doesn't hydraulically fracture the reservoir, so you're limited by the depth and the stresses you find at those depths, so that has a finite value. And so this is affected by changes in chemistry, affected by dissolution or precipitation, and I guess that would also change perhaps the heat rate coming out. And of course, one of the things that people have talked about in terms of allowing you to keep the temperature up is by using flow diverters. And so, for instance, at Newbury Volcano, which is in Oregon, dormant volcano where Altarock had their Newbury Mountain project, they had TZIMs, temporary zone isolation materials. And so what they were slurries of carbonate minerals that would go into the cold fractures. When they went into the cold fractures, they would solidify and stop flow into those fractures. And then as the temperature of those fractures came up again, rebounded, because now the heat that was in the rock, trapped in the rock, had a gradient towards the fracture, but now you've shut off the fracture by no fluid going in it. It would build up temperatures next to the fracture. The temperature of the temporary zone isolation materials would increase. They'd redissolve in water, be carried out of the fracture, and now that fracture would be open again to be able to take fluid afresh at the same time that you'd have been able to open up fractures in the other parts of the reservoir to be able to accommodate it. And so those are the kinds of interventions that can be used that would use geochemistry to look at this. So those are the mechanisms by which we might want to be interested in the geochemistry of these reservoirs. So from Glassley's book, this is a table that talks about the different characteristics of the dissolved components in the waters. They tend to be, in terms of pHs, they tend to be largely basic. Some are acidic. But the concentrations of these fluids are pretty high. So if you look at sodium chloride, sodium, potassium, calcium, and magnesium, seawater is something like 35,000 milligrams per kilogram. So milligram per kilogram, as we'll talk recently. So it's milligrams of dissolved components per kilogram of water. And so typically, since we're talking in terms of this being water, this would be 1,000 grams. So 1 milligram would be 10 to the minus 6, or it's parts per million. So this would be 62 parts per thousand. So 62,000 parts per million be 62 parts per thousand. So these are pretty high. And so this is just by virtue of the fact that the waters have been in situ for a while. They've come to some equilibrium. They're at elevated temperatures, and so are able to dissolve at relatively large concentrations. And so these magnitudes of dissolved concentrations may affect the characteristics of your reservoir as you start moving them around, and especially bringing them up on the surface and having them interact with the piping and plant, especially plant that it goes through turbines. So in terms of definitions of concentration, milligrams per kilogram or milligrams per liter are parts per million. Micrograms per kilogram or micrograms per liter would be 6 off that. So these would be parts per billion. You can also define them in terms of equivalent weights and using the, I've never used this as an equivalent weight. Milliequivalents would be basically in moles per liter of water. So concentration in milligrams divided by formula weight would give you moles. And if it's per liter, then that's moles per liter. Sometimes that's referred to as molality. And sometimes it's defined in terms of molar volumes or molar volumes. In both cases, they're defined by the number of moles you have in solution, moles of a solute per amount of solution. The only difference is that this is moles of solute in a single liter of water, but this would be moles of solute in the complete mass of both solute and solvent combined. So these are used typically the assumption is that these are in relatively small amounts of mass per unit mass, so that changes in the size of the amount in the system doesn't alter the amount of solvent that's there, their ratio. But in cases where you have very high concentrations of these components, it matters whether you take into account it's no longer dilute suspension, and you have to treat it as a concentrated suspension, and in which case you might want to use molar volumes as the component. If you look at equilibrium chemistry in terms of liquids, you can define any reaction in terms of these different components. So instead of muddying the waters by using sodium and chloride as these individual compounds, we can define the individual components, a reaction between components A and B turning into products C and D. And if the reaction is reversible, we also have the products C and D converting into the initial components A and B. So this is a stoichiometric equation where we define the number of these individual components that balance to get the right number of moles as we go. So these are balanced in terms of moles. And so if we look at the combination between compounds A and B in producing C and D, when it's at equilibrium, there's exactly an equal flow between the forward reaction and the reverse reaction. And the stoichiometry of these integer values, which define how much of each of these components, when combined, make how much of these individual components on the right-hand side. If we look at the rate at which this forward reaction goes into the second two components, we can define that rate of reaction in terms of an equilibrium coefficient, where these represent the concentrations of A and B, or number of components of A and B, usually in terms of moles, where the stoichiometric multipliers now become exponents applied to this. And so if we do that for the forward reaction, which is R1, and the reverse reaction, which is R2, we end up with these two individual components. These are the concentrations of these individual components in moving back from this to this state. And so at some stage when this is in equilibrium, we're making as much C and D as we are in reverse reaction A and B. And so in that particular case, we can take these two components and equate them to each other. And if we equate them to each other, these should be exponents, not multiplied by C and D, where we hope to know the rates at which we have these forward and reverse reaction rates occurring. If we divide them by each other, where the rates of production and of both sides of the reaction are the same, then this is equal to the dissolution rate, and it gives an equilibrium constant which we can define. So if we know what these individual components are, we can define the equilibrium coefficient, which is the rate at equilibrium that we're producing these individual components, and therefore we can decide the rates at which this compound will build up in the reservoir per unit volume of the fluid which is there, which is what we'll use it for. So these can be defined as a function of these individual components within the reaction. And so the utility of doing that is if we take the data from this previous table, and so the rates of concentrations and temperatures which were represented in that first table that we looked at are given here for geothermal fluids at these multiple different sites. And we can take two different compounds, sodium chloride being halite and quartz, SiO2, and we can look at the magnitudes of these equilibrium coefficients which describe the rate at which precipitation or dissolution would occur within these systems. And so for halite, we have magnitudes of these. I guess first of all we see that if you look at halite at increasing temperature, this equilibrium constant, they change fundamentally in different ways. As you increase temperature, the solubility of quartz increases. So this is increasing solubility. So water would progressively take more and more quartz as you heat it up. And halite is the opposite. It takes less and less halite as is able to stay in equilibrium water as you move up here. And so this would represent the equilibrium solubility of halite at these particular temperatures. So its equilibrium solubility is given by this coefficient, this magnitude. If you're above this or below it, you're either supersaturated or undersaturated relative to these. And so we can use these magnitudes to determine exactly what the equilibrium solubility would be. And so I did it in terms of sodium chloride first. So if you take sodium chloride, for instance, at 100 degrees centigrade, the log solubility is 1.6. People looking around like they are at airports for a plug to plug a computer in. I guess that was someone at the back. I don't think he's in our class. And so log K is equal to 1.6, so you 10 to the x that, and you find out that the value of this is 40. So the magnitude of this is 40. And so from that previous expression that we just had, sodium and chloride, stoichiometry of them is 1 to 1 as we go there. So their exponents are to the power 1. The value of K is 40, which is equal to this equilibrium constant here. And so this is the concentration of each of these together. So it's squared. So the concentration in terms of moles squared would be 1 mole of this and 1 mole of this. And so if this is equal to 40, then the number of moles which are present would be equal to the square root of this. The whole thing, right? Just doing that. That's all. And so that means that 6 moles of sodium chloride and 6 moles of sodium and 6 moles of chloride would be present in solution within a liter of water. And so if we look at the individual weights of those, since the weight of sodium is 23 grams per mole, and so 6 moles of this would be roughly 150 grams. For chloride, the periodic table weight, molecular weight is 35 times 6, which is 210. So if you sum those two together, it's something like 360 grams. So if in 1 liter of water you had 10 grams of sodium chloride, the equilibrium concentration that it can handle is 360 grams. So this would be undersaturated. It would dissolve the sodium chloride that you put in there, and it would go to no solid sodium chloride. It would all go into solution. And so you can define whether it will be undersaturated or oversaturated or at equilibrium by looking at the concentration relative to equilibrium. Conversely, if you take quartz at 100 and you look at the value of log K is -3, which is equal to 10 to the -3. And so this is 0.001. If you have 10 grams of silica in water at 100 degrees centigrade, then this would be the solubility. Quartz is, the stoichiometry is 1 to 1. So this is the component here, so you don't have to square root it. So you have to look at the individual components of the silica and the oxygen. 28 grams of silica, molecular weight 16 times 2 would be 36, 38, 32. And so 32 plus 28 is 60. And so the equilibrium concentration would be 60 grams per mole. But the solubility that's multiplied by this is the value of R times this concentration. So if you multiply that by this, it's not correct, is that at equilibrium, the solubility would be 0.06 grams. And so if you have 10 grams of silica in water, it is only able to take 0.06, and so it would leave most of that quartz in its solid state. It would be, it would take, I guess it would leave 9.94 grams in solid state and take 0.06 grams and put it in solution. So we can always define exactly what the equilibrium situation is if we know what these solubility constants are, and we know what the temperature is, and we have behavior here which is retrograde solubility. So as you increase the temperature, it takes less and less dissolved in water, and so-called prograde solubility. Where as you increase the temperature, it is able to dissolve more and more material because it has more capacity in the water to take it. In this, as you increase the temperature of the water, it has less and less capacity to be able to dissolve the solid into it. And so these fundamental behaviors have different consequences, I guess, for behavior within geothermal reservoirs. And it's given by the shape of these curves, one decreasing with increasing temperature and one increasing with increasing temperature. So if we take these, so this graph tells us something about these behavior in terms of retrograde and prograde solubility. The other behavior that describes what's going in the reservoir, which is related to this, is whether reactions evolve spontaneously or not. And so we talked about this in terms of, when we talked about thermodynamics, we talked about Gibbs energy, Gibbs free energy. And we could define what happens to a reaction is it progresses if this is negative, if it's less than 0. And we can define it as a change in enthalpy and absolute temperature and entropy. And so the best way to explain this is to, I think, look at this. And that is, if you want a reaction to proceed, then this value of delta G, which is Gibbs free energy, you want it to reduce. It has to be negative. And so physically, what that means is that if you want to go from your initial state, from your reactants, A and B, to your products, C and D, you want this delta G term ultimately to be negative, to go from here to here. It may well be that to get to this point, it has to go through some kind of activation energy threshold to be able to get to the place where it can go down. So this bump may be a big bump as it's shown here, or I guess it might not be there at all, or it could be a small bump to get to this position. In all of these cases, because the products have a lower free Gibbs energy than the initial reactants, this will always happen so long as you can get it across this bump. If the flow as you go from the reactants to the products is in the opposite direction, that the Gibbs free energy delta G is positive, then you're always going to have to supply energy into that system. You maybe have to supply more energy than you need because you get over this activation barrier, or you may be able to get directly to this by supplying enough energy but not going through an activation barrier like this. So these would be the corollaries of this. This proceeds directly. If you create enough energy into the system, this has to go through the boundary. And so this defines these 4 different zones. So in this particular case, if the change in entropy is greater than 0, so this is positive, this would be negative. If delta H is change in enthalpy is less than 0, then this would be negative change, and this would be positive. And the reason for writing it this way is that if this is negative and this is positive, it will always go, this will always be negative. So this would be the case where we spontaneously go from here to here without having to go through this edge. It's guaranteed that we can go directly to these. So if you look at this one here, so if enthalpy change is negative and entropy is positive, this is temperature, always in Kelvin, always has to be above 0. So this is always positive, not a change, but absolute. So to make this negative, then we have negative enthalpy and positive entropy. So negative entropy, so did I do that wrong? Spontaneous at all. So delta H is negative. So this has to be positive. So this one will always end up moving, always occur. So we don't have to put any energy into this system to make it go from here to here because we're always going down here. We don't have to go through this activation energy. Conversely, if this is positive, if this is positive, and this is negative. So that quadrant is given by positive and negative. So this is here. So this is always going to be this. So to go from here to here, it always has to be has to have energy added into the system to make that reaction. And the off-diagonal terms are when the combination between these two are not favorable to this always being negative, but depending on the magnitudes of entropy and enthalpy change, as they balance, when they balance sufficiently through the magnitude of temperature in the system, that they ultimately will give you a negative value. So you end up with this. So in other words, in this case would represent the case where you have to modify it through this activation barrier to ultimately get here. But if you're not able to get across this energy barrier, then you can't get to that position. So that's a way of defining it. The main point of what we're chatting about was from that previous figure that we had some cases representing retrograde solubility, less capacity with increasing temperature, and more capacity in the water with increasing temperature. So if you look at what the effects of that would be on a reservoir, what we could do is we could choose 2 temperatures that we might expect to find the reservoir at and look at the magnitudes of what the solubilities were. In other words, we just calculate the solubilities in this from these coefficients. The natural solubility was equal to 0.6 grams per per liter or kilogram at equilibrium. So this is the solubility at that particular temperature, which for us was 100 centigrade, I think. So we can look at how the solubilities would change as you go for a prograde system in this particular case. So for quartz in a reservoir at 250 degrees centigrade, it would take something like, this would be 8 millimoles per kilogram at 250 degrees centigrade. But if we change the temperature to 100 degrees centigrade, it only takes something like less than 1. So millimole is a mole times 10 to the minus 3 at 100 degrees centigrade. So as you increase temperature, as you go from one to the other, you're able to take a larger amount of the component dissolved in the water. The converse of that would be retrograde solubility. We used halite before, but calcium carbonate within a system is one such reaction, and we have the opposite occurring here. If you go at 250 degrees C, we have something in for millimoles in water. We have, so this is brine. These are all brines. This is pure water. So if you flash it to steam and re-inject it after condensing it, you might expect that it didn't have very much dissolved material in it, and so it would go back in as basically just distilled water. So this is 2, this is 1, this is 0.5. So this is less than 0.5 millimolar per kilogram. And if you look at it at 100 degrees centigrade, then it's 5.5 millimolar per kilogram. So what we could do is we could use those as type behaviors for two interesting compounds, quartz and calcium carbonate, that might be present in reservoirs, and to see what that would say about what happens as we transfer them across the system. So if you imagine taking fluid at 250 degrees centigrade and say it's a mixture of a reservoir which is both quartz and calcite in the reservoir, then the equilibrium concentrations dissolved in water for these are exactly those concentrations that we've defined here, which are these. And if in going across the reservoir to some other location where it becomes 100 degrees centigrade, the magnitudes of their solubilities change, and so the ability of water, which might be saturated in one of those components, to hold it, in the case of quartz, which is prograde soluble, as the temperature drops, it would lose 8 millimoles per kilogram of water in the system as it goes across here. But for calcite, and it would put that as solid material into the reservoir, and for calcite, which is present at 250 degrees centigrade at only half a millimole, if the reservoir happened to have calcite in it, calcite veins, it would dissolve that up to a maximum capacity in the water of 5.5 millimoles. So it could take roughly 5 millimoles as it went across. So that's basically the kind of calculation that we'd like to be able to do. So if you look at a realistic reservoir, the reservoir here is where you re-inject water into the system. It flows across the reservoir, is transferred from cold water as it comes in to being hopefully hot water as it comes out. It's taken out of the system, hot. It's flashed to steam through a turbine to generate electricity, and then condensed and put back into the reservoir. So if you go through that cycle, we kind of have everything we need to be able to say what's going on with that. If we look at the transmission across the reservoir, we know how to do that. We use Darcy's law. We can get the volumes or the volumetric flow rates defined by the pressure gradient across the reservoir. So if we know the pressure gradient between injection and recovery wells for either a very simple one-dimensional geometry or a more sophisticated geometry, as we talked about in terms of flow nets, where we could work between equipotentials. We can go like this. So we can do that in a variety of ways of different sophistication in looking at flow rates through this system. This is the simplest here. So we know the flow rates across the system. We know as we flow from upstream to downstream that we have this behavior that we spent a little bit of time talking about. And just to remind ourselves, we made the case, this was kind of bass-ackwards. Here we're doing the opposite. We're injecting hot water into a cold reservoir. And so that hot water in a cold reservoir will be chilled as it goes from inlet to outlet. And we made the point that there's the rate at which the front moves, which is the advective front. So the advective velocity is equal to the Darcy velocity, which you get from Darcy's law, divided by the porosity of the reservoir. So because porosity is always less than 1, typically it might be 10%, so it's 0.1. So this could be 10 times the Darcy velocity. That gives the location of this inflection point here. And this second inflection point represents the case where the influent fluid that's come in up to that period of time, which has reached this location here, all of the thermal energy that's been transferred to that fluid has been recovered from this orange portion of the reservoir. It's taken all the thermal energy from here, and that would be present in the fluid, which now extends to this point here, but it's kind of smeared in this zone here because this is a place where here the reservoir temperature would be brought up to the injection temperature. Here the reservoir temperature would still be 0, and in between here, part of the energy of the flowing fluid would be mixed between the reservoir and the fluid itself. And so we know that this would be the temperature profile as we go from upstream to downstream, except in our particular case, if we looked at the water temperature, we're injecting cold water. Cold water is heating. And as we come out, it's coming out hot. And so that's the fluid temperature. The reservoir temperature would be I guess this is reservoir temperature. Cold fluid heat, yeah, so reservoir temperature would be cooled. Yeah, actually the reservoir temperature would be the same. It would follow the same trajectory, right? It would still be hot here because now the hot water has robbed all the heat from this part of the reservoir. It's brought it up to this temperature, and it's coming through the system at this temperature here. So we'd expect to see this temperature gradient in the fluids and the reservoir as we go across it. And so what the implications of that would be for the chemistry are that as you go across the reservoir, you start off cold, may not be 100 degrees centigrade. At Forge, for instance, the injection temperature is whatever fluid you can get the fluid down to. In a recent circulation test, it was 38 centigrade. I think also this is the boiling point for IPA. So if you run your geothermal fluids after you flash it to steam and condense it at 100 degrees centigrade, you can put it through an organic Rankine cycle plant, which boils isopropyl alcohol. Its boiling point is 38 degrees centigrade, and it changes phase from a liquid at any temperature above 38 degrees centigrade. So in a closed system, you can run that through a turbine and generate electricity. So you have to have a phase change to run a turbine. If it's water being flashed to steam, it has to be 100 degrees centigrade at atmospheric pressure. But if you use a different closed system with a lower boiling point liquid, then you can also run that through a so-called binary plant. But I digress. So if you go across your reservoir, it starts off at injection temperature. It picks up heat from the reservoir as it goes across the reservoir. It comes in and is recovered at the exit temperature of the reservoir. And so in this particular format, if it comes in with zero concentration of silica, it will dissolve silica and it will dissolve it up to the maximum magnitude that it can take. The maximum magnitude it can take will be at 250 centigrade, 8 millimoles of silica per liter or kilogram of water. Calcite, if it starts off undersaturated, it may be able to dissolve some because it's present here at low temperature, and it can retrograde solubility means that the solubility at low temperature is quite high. So it could dissolve material from the reservoir if it starts off at 0 millimolar. But if it dissolves it and then works its way across the system, as the temperature changes to be warmer, then it can't contain the same amount of calcite as it did at a lower temperature. And so even though it would dissolve it from this part of the reservoir and bring up the concentration within the water to some magnitude, it would have to deposit it as it came to the other end of the reservoir because the water is hot and it drops it out of solution. So that's what's going to happen within the reservoir. You could be dissolving retrograde minerals close to injection and then precipitating them close to recovery at higher temperatures. If you come in at low concentrations of prograde minerals like quartz, then you'll dissolve them throughout the reservoir. They're not very soluble, so you might not reach the maximum concentration that we talked about at 250, which isn't a very, well, actually it is a reasonably high concentration. You might not reach this, but it will be building concentrations as it goes across the reservoir. So this potentially comes out at a high concentration. This potentially comes out at a low concentration, the water, because it's dropped it in the reservoir. And so when you bring it out of the reservoir, these might be the concentrations you have. You flash it to steam. If it goes from water to steam, it doesn't carry any of this, so it deposits it. It deposits it either in the piping to get to this, or it deposits it disastrously on the turbine blades and destroys it through that. And then it comes out as a vapor on the other side. You condense the vapor. The vapor should start off with very low concentrations of those as it goes through. So I guess there's two important things to talk about here. One is what this is doing to the reservoir. So this affects our energy out of the system is equal to the mass flow rate, specific heat capacity, and the temperature. We want to have it build temperature as it comes across to be able to satisfy this. We want to have a large mass flow rate as we come across. If we precipitate calcite at the exit point of our reservoir, even if we've opened up pores and fractures at the injection well, this isn't going to be very good for maximizing our mass flow rate because we can only apply a certain delta P across the reservoir because this delta P is limited by a maximum that we can apply here, not delta P, but a maximum absolute pressure before we hydraulically fracture the reservoir. And using a larger delta P means that pumping costs, parasitic costs will be higher in running our system. So we're interested in what it does to the reservoir, but we're also interested in what it does to the equipment when it comes off. And so you might acidize it to be able to make it drop the silica out of the system as it comes out, to be able to pre-treat it. So that's why we might be interested in geochemistry in our reservoir. We won't dwell on this, but the big picture, actually this is the big picture here. Yeah, this is a big picture. Actually this is, if we look at the heat rates out of our system, as being this. So if we want to be able to characterize this full system, we need a big flow rate, we need to have the fluid coming out, whatever the fluid is, that doesn't change much, and we want it to heat up enough temperature. So we need to solve three systems. The flow rate across the system is given by Darcy's law. Simple models would give us a core, and we could calculate exactly what this volumetric flow rate would be if we knew the pressure gradient, cross-sectional area of flow, and the characteristics of permeability, probably for single-phase flow in these systems. The majority are single-phase flow. We talked about multi-phase. In flowing across this at some velocity, we want to make sure as we go across this system that the temperature regime goes from cold water injected to hot water out. And so that will depend on robbing heat from the reservoir and transporting it across to the other side. And in going across the reservoir from a cold upstream to a hot downstream temperature at recovery, then we think that that's going to do some interesting things with the geochemistry. And the transport of components dissolved in water is not unlike the behavior of fluids going across the reservoir and transporting heat, picking up a quantum of heat from the reservoir, and then physically moving it along in that fluid until it comes out at the outlet, so-called advective flux that we talked about. And so these three behaviors together are the intrinsic physical processes that govern transport and behavior of our reservoir. And so this isn't a modeling class, but a very simple exposition of that model would be to look at transport between upstream injection and downstream recovery as you go across here. So this would be the upstream. This would be at high pressure. This would be at high temperature. And the concentrations we don't know. And this would be at low pressure, low temperature, and concentrations we don't know. And so in all of these, we use conservation equations. And so to link all these together, a generic conservation equation is defining mass transport within the system. So a conservation equation takes a bucket, differential bucket, and looks at the density, the mass of fluid within that bucket. So if you put more mass of fluid into that than you take out, then you accumulate mass, and that accumulation is given by this term as a result of the mass rate in versus the mass rate out being balanced with the accumulation. And so this is a generic conservation equation that we can apply both to mass flow of water, flow of a quantum of heat energy, and flow of mass of dissolved minerals. Generically, we can use this expression. And so if we use this expression but just use different dependent variables to represent these three processes, so the three processes will be Darcy's law for fluid flow, Fourier's law for temperature, and Fick's law for diffusion for mass transport of components dissolved in water. And so this is just a quick exposition to take this relationship for mass balance, put in either Darcy's law or Fourier's law or Fick's law into this conservation. Slightly different, but if you put Darcy's law in here, then you get this expression here, which we've seen. This is Darcy's law being put in on this term here. This is manipulating this to show that it's actually a function of compressibility and getting this term in terms of a change in pressure due to compressibility. So if you substitute these, you end up with a one-dimensional equation, which is fluid flow in versus fluid flow out. The imbalance between those is an accumulation of fluid or a depletion of fluid in the system. through the compressibility of the system, not specific heat capacity. If you look at the flow of mass within the system, then you can take the same conservation equation. The rate at which mass travels in the system by diffusion, Brownian motion, is given by Fick's law. This is a diffusion coefficient in terms of meters squared per time second, and a concentration gradient. This is the advective flux, a concentration or a mass of fluid carried by the velocity of the fluid downstream. If you put those two components into this conservation equation, you get another diffusion-like equation. Mass of solute into the system versus mass out driven by diffusion balances with the mass carried into the system versus going out due to advection, carried with the bulk motion of the water. And the imbalance between these is an accumulation of mass within the system, given by the concentration of that particular solute in water. And the heat flow means that we just put Fourier's law into this expression and balance it. We've seen it before also. And if we do that, Fourier's law is that the heat flow is a function of the temperature gradient in space and thermal conductivity. It flows in the opposite direction that this gradient is positive, hence the negative in all of these components. And the advective flux is just the velocity of flow and the heat content. The heat content is the density, specific heat capacity, and temperature. If you throw both of these into the conservation equation, you end up with a heat diffusion equation. Heat that travels by conduction, heat that travels by advection, in versus out in each of these terms, and the imbalance between in and out is the accumulation or depletion in the reservoir. And so all these equations look exactly the same, and if we write them in terms of the accumulation term, the advection term, and the diffusion term, this diffusion term takes different forms, either for temperature, concentration, or pressure, and we can solve them. And that's all that these numerical models do, is they write the three basic equations, they put in the appropriate coefficients, and they solve them for the changes in these dependent variables in the system. So you solve for changes in pressure throughout the system, changes in temperature throughout the system, and changes in concentration. And you can use sophisticated models to look at spatial changes of these variables as you go through them. Or you can also just use Darcy's law, Fourier's law, and Fick's law to be able to come up with back-of-the-envelope solutions, which is what we've done so far. Maybe I'll start. I do want to say some more about that next time, but I don't have time to do that. So we've basically solved all the physical components that we want to be able to describe behavior in our system. We've made the case that to get heat out of it, we have to have high flow rates, sustained temperatures, and we don't want to destroy the permeability of our reservoir because that affects the flow rates of the system. So that's the most succinct way that I think I can state this. Next time we'll talk about geochemistry in terms of some practical. We'll finish off talking about this modeling. We'll go back to talking about how we can calculate the distribution of these coefficients very briefly, and then we'll talk about some practical ramifications for real reservoir rocks and real experiments in looking at dissolution and precipitation and changes in permeability in those systems. And then after that we'll start talking, I think, about methods of geological and geophysical prospecting involving drilling and geophysics, basically. So that's where we are in the class. So I'm going to stop there. Thanks very much.